Early physicists assumed molecules behaved like rebounding balls, thus explaining the pressures exerted by a gas, but they could not explain the forces that hold them together. For a long time, physicists were governed with their same ideals until German physicist Max Planck began the era that showed the properties of atoms and molecules were not held by the same physical laws as larger objects. It is then that Planck found that atoms and molecules emit energy in specific quantities or quanta. Having an in-depth knowledge about the nature of waves is needed to better understand Planck's quantum theory. Waves can be described as a vibrating disturbance by which energy is transmitted. Think of water waves, for example. Waves are characterized by their length, height, and by the number of waves that pass through a certain point in 1 second. Wavelength is the distance between identical points on successive waves. The frequency is the number of waves that pass through a particular point in 1 second, and the amplitude is the vertical distance from the midline of the wave to the peak or trough. In short, wavelength expresses the length of a wave or distance over wave. Frequency indicates the number of these waves that pass any reference point per unit. Length can be expressed in units of meters, centimeters, or nanometers. And frequency is measured in hertz, where 1 hertz equals 1 cycle. There are several types of waves, like water waves, sound waves, light waves, and electromagnetic waves that can travel 3.8 times 10 to the 8th power meters per second, or to be easier, 186,000 miles per second in a vacuum. Knowing what we know now on waves, we are able to move on to Planck's quantum theory. The amount of radiant energy emitted by an object of a certain temperature depends on its wavelength. Planck stated that atoms and molecules could emit or absorb energy only in discrete quantities. Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy of a single quantum of energy is shown by E equals hv, where h is Planck's constant, 6.63 times 10 to the negative 34th joules times second, and v is the frequency of radiation. It is also important to note that energy is always emitted in integral multiples of hv, such as hv, 2hv, and 3hv, and can never be shown as 1.6 hv, 2.72 hv, or 5.96 hv. After Planck presented his quantum theory, Albert Einstein tackled another scientific mystery known as the photoelectric effect. This, a quantum phenomenon in which electrons are ejected from the surface of certain metals exposed to light of at least a certain minimum frequency, called the threshold frequency. Although the number of electrons ejected was proportional to the brightness of the light, the energies of the ejected electrons were not, and below the threshold frequency, no matter how intense the light, no electrons were ejected. Einstein assumed that a beam of light was really a stream of particles, calling these light particles photons. He assumed each photon must have energy, shown by E equals hv, where v is the frequency of light. Electrons are held in metals by attractive forces, and removing them requires high frequencies of light. If the frequency is equal to the energy that binds electrons in metal, then the light has enough energy to free these electrons. If the frequency is higher, these electrons may even possess kinetic energy, shown by hv equals ke plus w, where ke is kinetic energy of the electrons and w is the work function. And if written as ke equals hv minus w, shows that the higher the frequency, the greater the kinetic energy of the ejected electrons. The more intense the light, the greater the number of electrons emitted by the metal. The higher the frequency of the light, the greater the kinetic energy of the ejected electrons. Einstein's theory possessed a dilemma, and the only way to work through that dilemma was to accept the fact that light possesses both particle-like and wave-like properties.
Emission spectrum, it's either continuous or line spectrum of radiation emitted by a substance. The same energy that is thermal energy or high voltage electrical discharge. With the emission light, you can see the atoms produce light with colors from red to violet, red being the strongest, and then goes down to orange, then to yellow, green, blue, and violet, which violet would be the weakest. Energies that are in an electron in a hydrogen atom can be occupied by the equation e to the n equals negative RH parentheses 1 over n to the square. RH is Rydberg's constant of the hydrogen atom, which is 2.18 times 10 to the negative 18 joules. And then the principal quantum numbers is n will equal to 1, 2, or even 3. With n equals 1 will be the most stable energy, also known as the ground state. Lowest, also known as the lowest energy. Example would be this. You see me right now? I'm at the lowest energy right now. I'm not doing nothing. Okay, and then n would equal to 2 or 3 would be the excited state. Higher energy will be greater than the ground state energy. Example would be this. You see me all going all crazy, hyperexcited? That's example of n would be n equals 2. Alright, and right here is the drawing of Bohr's model. With the n1, that would be the first ring of energy, n2 would be the second ring of the energy, and then n3 would equal to the highest energy. And with the highest state of energy, it would be further away from the nucleus. And with the photon, it goes to the lowest energy to orbit. So pretty much if it's at the highest energy state is 3, it'll go down to number 2. The difference in the energies of the initial and the final energy states that delta E will equal to E final minus E initial. With the tradition results in the emission of the photon of the frequency V and energies HV. So delta E would equal HV would equal to RH parentheses 1 over n squared initial minus 1 over n squared final and the parentheses. So an example would be RH would equal to 2.18 times 10 to the 18, and you're going to multiply that by the difference between 1 over 5 squared minus 1 over 2 squared. So after that, I got 0.21. So after that, you multiply that negative 0.21 times the 2.18 times the 18. And right there, you'll get 4.58 times 10 to the 19. Light waves can behave like stream of particles as photons. An electron bond to a nucleus behave like a streaming wave. So right here is an example of one wave. So it would be L would equal to lambda over 2. This one would be another example. Would be L would be 2 lambda over 2. And then this is the other one. Would be L equals 3 lambda over 2. So the dots right there would be nodes where the points that are at 0. So that's when they make no movement and all that stuff. So electron does behave like the standing wave hydrogen atom. The length must fit in the circumference. So this would be an example right here of how the electron would be moving.
This section is 7.5 quantum mechanics. So going back to Bohr's theory, it had many problems. One of them being that it could not be possible to specify the position of the wave because the wave extends in space. So Heisenberg made a uncertainty principle, which is called the Heisenberg uncertainty principle, which states that it is impossible to know simultaneously both the momentum, which is P, and you can solve that by mass times velocity, and the position of the particle with certainty. So it basically says that the position of the momentum and a particle cannot be accurately measured at the same time, and the two uncertainties are inversely proportional, which means that if the momentum and the position are the same, then it will give like 2 and 2, then it will give you 4. But if the momentum is bigger, then that means that the position has to decrease for it to get the same value, and so on. And this is the equation of the Heisenberg uncertainty principle. So the uncertainty of the position is represented by x, and the uncertainty of the momentum is represented by p. And the solution for the momentum and the position always has to be greater than or equal to h, which is Planck's constant, which is 6.6 times 10 to the negative 34 joules per times seconds, over 4 times pi, which is another constant, which is just to give a number. And also to calculate the momentum, the mass has to be in kilograms and the speed, which is u, has to be in meters per second. So as we apply this principle to the hydrogen atom, it is seen that the electron does not orbit the nucleus in a well-defined path as Bohr had thought. So we're going to have an example problem, which says an electron is moving at a speed of 8 times 10 to the 6th power meters per second. If the uncertainty in measuring the speed is 1% of the speed, calculate the uncertainty in the electron's position. The mass of the electron is 9.1094 times 10 to the negative 34th power kilograms. So we put in the speed, the uncertainty of the speed, and we multiply it by 0.010, which is the 1% that previously stated that said that the speed is 1% of the actual speed, the uncertainty. And we multiply it by the speed that was originally given to us, which is 8.010 times 10 to the negative 6 power meters per second. So we get the value, which is 8.010 to the 4th power meters per second. So then we try to find the momentum, which is the equation is p times n times u, which is the position times the speed. So we have to apply the uncertainty of the speed, so we get this value, and then we move it into the equation because we're trying to find the uncertainty of the momentum. So we plug them in, and so it's going to be 9.1094 times 10 to the negative 31st power kilograms times 8.0 times 10 to the 4th power meters per second. And our value that we're going to get of the uncertainty of the momentum is 7.3 times 10 to the negative 26 power kilograms times meters per second. So the uncertainty in the electron's position, which is the uncertainty of the x, we have to change the equation of the uncertainty, which is Schrodinger's principle, and we make it so that we're trying to solve for the uncertainty of the position, which is what we're supposed to find from the example. So we plug in a Planck's constant, which is 6.63 times 10 to the negative 31st power joules times seconds, over the 4 pi, and then we put in the 7.3 times 10 to the negative 26 power kilograms times meters per second, which we got from the uncertainty of the momentum. So when we solve that, it's going to give us 7.24 times 10 to the negative 10th power meters, which corresponds to 4 atomic diameters, which is going to be the uncertainty in the electron's position of the hydrogen atom. So our next subsection that we're going to be going over is the quantum mechanical description of the hydrogen atom. So although quantum mechanics says we can't pinpoint an electron in an atom, it does define the region where the electron might be at a given time. Square wave function defines the distribution of electron density in three-dimensional space around the nucleus. Regions of a high electron density represent in a high probability of locating the electron, whereas the opposite holds for regions of low electron density. So to distinguish the quantum mechanical description of an atom from Bohr's model, we speak of an atomic orbital rather than an actual orbit. When we say that an electron is in a certain orbital, we actually mean that the distribution of the electron density, or the probability of locating the electron in space, is described by the square of the wave function associated with that orbital. An atomic orbital, therefore, has a characteristic energy as well as a characteristic distribution of electron density. Schrödinger's equation makes nice for the simple hydrogen atom with its one proton and one electron, but it doesn't exactly mean that for the atoms with more than one electron. So fortunately, scientists have been able to use approximation. For example, although the behavior of electrons in many electron atoms is not the same as hydrogen atoms, we can use the energies and the wave functions from the hydrogen atom as approximations of the behavior of the electrons in other complicated atoms. So we have electron density, which gives the probability of an electron will be found in a particular region of an atom. And an atomic orbital is the wave function of an electron in an atom. And many electron atoms simply states that it's an atom that contains 2 or more electrons. So, in 1926, Austrian physicist Erwin Schrödinger used a complicated math technique to make an equation that describes the behavior and the energies of submicroscopic objects. Even though we will not discuss it yet, it's important that it corroborates both particle behavior and terms of mass and wave behavior. In terms of wave function, which is represented by psi, which depends on the location in space of the system, such as an electron of an atom. Schrödinger's equation began a new era in physics and chemistry, for it allowed a new field called quantum mechanics, or also called wave mechanics. So it uses both wave behavior, which is represented by psi, and particle behavior, which is measured as mass, and that creates the Schrödinger equation. 7.6 Quantum numbers. In quantum mechanics, there are 3 quantum numbers that are needed. And quantum numbers describe the distribution of electrons in hydrogen and other atoms. And those 3 quantum numbers are principal quantum number, angular momentum quantum number, and the magnetic quantum number. These numbers come from the mathematical solution of Schrödinger's equation for the hydrogen atom. They are these, as I had said, and these quantum numbers will be used to describe atomic orbitals and to label electrons that reside in them. And there is a 4th quantum number, which is spin quantum number, and that describes the behavior of a specific electron, and it completes the description of electrons in atoms. So our subsection is called the principal quantum number. The principal quantum number can have integral values, such as 1, 2, and 3, and etc. And it corresponds to the quantum number, the original one that we had just stated earlier. And in a hydrogen atom, the value of n, which is the principal quantum number, determines the energy of an orbital. But it's not the case for many electron atoms, which have 2 or more electrons. The principal quantum number also relates to the average distance of the electron from the nucleus in a particle orbital. The larger n is, the greater the distance of an electron in orbital form from the nucleus, and therefore the larger the orbital. So the farther the distance, the larger the orbital is going to be from the nucleus of the atom. And here we have the equation of the principal quantum number, and this holds only for the hydrogen atom. So our next subsection is the angular momentum quantum number. And this will tell us the shape of the orbitals. So if the angular momentum quantum number is equal to 0, we have an s orbital. If the angular momentum quantum number is equal to 1, we have p orbital, and so on. So the angular momentum quantum number values of the angular momentum quantum number depends on the value of the principal quantum number n. So given the value of n, it has the possible value integrals of 0. So that will be n through 1. If n is equal to 1, only one possible value of the angular momentum quantum number is there. And if n is equal to 2, then there are two values of the angular momentum quantum number, given by the numbers 0 and 1. And if the n is equal to 3, then there are three values of the angular momentum quantum number, which is 0, 1, and 2. And here is a chart naming the orbitals and the number of integral values that are given in each orbital. So S has 0, P has 1, D has 2, and F has 3, G has 4, and H has 5 integral values. A collection of orbitals with the same value of n is called a shell. One or more orbitals with the same number of the orbitals values are referred to as a subshell. So for example, if the shell n equal to 2, it will have two subshells of the quantum number of 0 and 1. These are called 2s and 2p subshells. 2 comes from the value of n, and s and p come from the values of this. Our next subsection is called the magnetic quantum number. So the magnetic quantum number describes the orientation of the orbital in space. Within a subshell, value of the magnetic quantum number depends on the value of the angular momentum quantum number. For a certain value of the momentum quantum number, there are two angular momentum quantum plus 1 integral values of the magnetic quantum number. So the values of the magnetic quantum number depends on the value of the angular momentum quantum number. So for a certain value of the magnetic quantum number, there is this equation for the integral values of magnetic quantum numbers. So if the angular momentum quantum number is equal to 0, then the magnetic quantum number will equal to 0 as well. But if the angular momentum quantum number is equal to 1, then you plug in the value into the equation that was given, and that will give you the three values of the magnetic quantum number, which is going to be -1, 0, and 1. And if the angular momentum quantum number is equal to 2, then you plug in the value into the equation, and it will give you the five values of the angular momentum quantum number, which is going to be -2, -1, 0, 1, and 2. The number of the magnetic quantum number value indicates the number of orbitals in a subshell with a particular angular momentum quantum number value.
Orbitals are a region of probability where electrons can be found. There is s, p, d, f orbitals. We use the quantum numbers to determine energy level, orbital type, specific orbital, and spin of an element. More electrons means more orbitals. To determine orbital type, look at the angular momentum quantum number. If the angular momentum number equals 0, it is a s orbital with one energy level and has a spherical look. If L equals 1, it is a p orbital and it extends out in 3 axes. If L equals 2, it is a d orbital, and if L equals 3, it is a f orbital. Electron configuration helps determine the valence electrons on an atom. Valence electrons contribute to the unique chemistry of each atom. When describing an electron configuration in terms of the orbital diagrams, that allow us to see where the electrons in an atom are. The arrangement of electrons in the energy levels, sublevels, and orbitals of an atom. The Pauli exclusion principle states no two electrons in an atom can have the same set of 4 quintrum numbers. A maximum of 2 electrons may occupy an atomic orbital, but if they have opposite spins. Hund's rule specifies the electrons occupy equal energy orbitals. Energy levels are represented by the coefficients. Sublevels or orbitals are the letter symbols. The number of electrons in a sublevel are superscripts. Okay, good. Electron configuration, we use our periodic table from left to right and up to down. This helps us see how electrons are arranged for specific element shells. Each orbital holds 2 electrons. So the number of orbitals in S sublevel is 1, so there's 2 electrons. The number of orbitals in any P sublevel is 3, so there's 6 electrons. The number of orbitals in D is 5, so there's 10 electrons. And the number of orbitals in NEF sublevel is 7, so there's 14 electrons. Now, to find the electron configuration of chlorine, we write 1s, 2s, 2p6, 3s, 2, and 3p5. This is the full electron configuration. To use the condensed electron configuration, you go to neon, right here in noble gases. And write 2, 3s, 2, 3p5 for your condensed. Electron configuration.
Alpha principle dictates that as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the atomic orbitals. The electron configurations of all elements except hydrogen and helium are represented by a noble gas core, which shows in brackets the noble gas element that most nearly precedes the element being considered, followed by the symbol for the highest filled subshells in the outermost shells. For example, boron is represented as He2s2 2p1, and tin is represented as Kr 5s2 4010 and 5p2.
Transitional metals either have incompletely filled D subshells or readily give rise to cations that have incompletely filled a subshell. Electrons in the same subshell, d orbitals, have equal energy but different spatial distributions. Electrons are more strongly attached by the nucleus when they have the 3d5 configuration. Extra stability is gained by having half-filled and completely filled subshells.
Lanthanides, or rare earth metals, have incompletely filled 4f subshells, or readily give rise to cations that have incompletely filled 4f subshells. The added electrons are placed in 4f orbitals, and after it is completely filled, the next electron enters the 5d subshell. The last row of elements is the actinide series. These elements are not found in nature but have been synthesized.
Example. Okay, so example. What element is represented by the following ground state electron configuration? So 1s squared, 2s squared, 2p6, 3s squared, and 3p4, which the answer should be sulfur. And the other example is gonna be brackets xe 6s1 for f to the 4th power and fd to the 10th power. So the answer right there should be gold.